Hello again, and it's physics time. This is video lecture 19.3, and we're going to skip over a couple of sections in chapter 19 and go to sections 7 and 8. That's the topic of this video lecture. Section 7 is titled The Molar Specific Heats, plural, of an ideal gas. And section 8 is Degrees of Freedom and Molar Specific Heats. I'm going to take the content from those two sections and combine them into one video here. The upshot, the key idea of this video is pretty straightforward to say in words. We're interested in a dilute gas in a container, ideal gas. We're going to add energy as heat, Q, and we want to know how much the temperature will change, delta T. That's it. Now, what's important to keep track of is a couple of things. What kind of gas is it? What are the constituent particles? What are they? Are they single atoms like helium? Or are they molecules like hydrogen gas, which is diatomic? And what is the condition of the experiment you're going to do? Specifically, we're going to look at two conditions. First, we hold the volume of the gas constant while we add the heat Q and then see what the temperature change is. Second, instead of volume constant, we hold the pressure of the gas constant. Add the heat energy Q and see what the temperature change is. You can think about our little cylinder apparatus for doing experiments with an ideal gas that I introduced in chapter 18. And we should be able to visualize how we would do these experiments. Constant volume, put the locking pin in place so that piston can't move. Right? That's it. Constant pressure, take the locking pin out. Then the pressure is controlled by how many little lead shots are on top. If you want the pressure to be constant, don't touch the lead shots. That's simple. Okay? All right. Simple in words, but let's start getting into the details. So the two key ideas we're going to talk about in this video are something called the equipartition theorem. Theorem means it's something that can be proved. We won't go through the proof here. You take Physics 320 if you want to see that. And the concept of molar specific heat, which we actually already introduced in chapter 18 when we talked about absorption of heat. And in chapter 18, we said you can have what's called specific heat or specific heat capacity, which is conceptually heat capacity over mass of a sample. Or you can have molar specific heat or molar specific heat capacity, which is heat capacity over number of moles of the gas. We're going to be working with molar specific heat capacities in this section because it turns out there's a very simple formula for molar specific heats, and that's what we're going to get to now. We need this result called the equipartition theorem, proved in the 1800s by James Clerk Maxwell. That's how you pronounce that. And here's what the theorem says. Every molecule has a measurable number of degrees of freedom, F. So F is a number, an integer. 1, 2, 3, 4, 5, 6, 7, 8, 9. F denotes how many degrees of freedom a molecule has. What's a degree of freedom? Well, loosely speaking, it's a way of storing energy, although I'm going to get more specific than that. Okay, so we'll have to know how many degrees of freedom a molecule has. That will be important in the equipartition theorem, because the theorem says, here's the actual statement of the theorem. With each degree of freedom, there is an average energy per molecule of, that's a very famous result I just highlighted there, 1/2 times that constant Kb. Remember, that's the symbol for Boltzmann's constant, times the absolute temperature in Kelvin, big T. For every degree of freedom, the average energy of a molecule is 1/2 Boltzmann's constant times the temperature. Very famous result. If anybody does advanced study in physics, and listen to people give talks at higher levels in physics, you will hear them say quite frequently things like 1/2 kBT, 1/2 kBT, 1/2 kBT. As we all know, 1/2 kBT. Okay, it shows up constantly. So we're going to use it here. But what's important is to know how many degrees of freedom the molecules have, because they have that much average energy, 1/2 kBT, for every degree of freedom. So we have to be able to determine how many degrees of freedom a molecule has. Now I'm going to talk about that with this picture below. I realize the print's a little bit small, so I'm going to annotate it as I go, hopefully making the print big enough for you to see. But this is all about determining how many degrees of freedom a molecule has. A degree of freedom, another way, a little bit more of an explicit way to describe degree of freedom, is any form of energy that can be written as a function of a position coordinate, a linear momentum component, or an angular momentum component in the following way. So E here stands for energy. The energy can be written as a constant times the x coordinate squared, or the energy can be written as a constant times the x momentum squared, or the energy can be written as a constant times the x angular momentum squared. The B, C, and D there are all constants. Or E equals constant times y squared, or E equals a constant times py squared, or E equals a constant times ly squared, or z's. The point is that the energy is proportional to either a position coordinate, a linear momentum component, or an angular momentum component squared. That's the key commonality here. The energy is proportional to one of those quantities squared. And every term in the energy that goes like one of those terms squared represents a degree of freedom. So let's take an example. Let's take a diatomic molecule that exists in nature, hydrogen gas. Hydrogen in its natural state will have two hydrogen atoms bonding together to make a hydrogen molecule. And we draw in chemistry and physics a very simple representation of the hydrogen molecule, kind of like a dumbbell or a barbell, where the two hydrogen atoms are represented by its spheres, and then there's a bond between them that we draw as a line. Okay? And I have drawn the hydrogen molecule in this dumbbell picture with the bond along a z-axis, and then an x-axis perpendicular to the bond, and a y-axis perpendicular to the bond. Okay? Okay, Vinny says yes. Now, let's keep track of the energy of this molecule. First, it can have what's called translational kinetic energy. Remember kinetic energy? 1/2 mv squared? Well, really, it's 1/2 m magnitude of velocity squared. So the translational kinetic energy, I'll write it over here to the side, is 1/2 m times Vx squared plus Vy squared plus Vz squared. And then all you do is a little trick. Remember the formula relating x linear momentum to x velocity? P sub x equals mv sub x. Similar one for y components, similar for z components. You can use that to write the k trans expression like this. 1/2m times px squared plus py squared, just fit this, I think, plus pz squared. And that's just from the molecule itself, the barbell, zipping around in three-dimensional space, x, y, and z. Translation is what that means. Just the molecule, its center of mass, is zipping around inside the container. Note then that there are 1, 2, 3 quadratic squared terms. So for the translational kinetic energy, from that, we get 3 degrees of freedom. So you'll see here that if that's all that was going on, then you would say F equals 3. There are 3 degrees of freedom from the translation of the molecule. However, a hydrogen molecule with its barbell shape with 2 spheres connected by a linear bond can do other kinds of motion besides just translating throughout space. It can rotate. So if my pencil here represents the bond axis of the hydrogen molecule, imagine a sphere. My fist here represents one hydrogen atom at that end and another hydrogen atom at that end. Okay? This represents the bond. It happens to be drawn along the z-axis. This barbell shape can rotate. Okay? And it can rotate about 2 of the 3 axes. It can rotate about the 2 axes that are perpendicular to the bond. So there's the up-down axis, that would be y in our picture. It can rotate about that, like so. Or there's the x-axis this way, and it can rotate about that, like so. And it turns out, you learn this from experiment, at the quantum level, that you cannot detect rotation about the z-axis. You cannot detect that in quantum mechanics. So there is rotational kinetic energy, rotational, and we have to account for that. At least there can be rotational kinetic energy, I should say. Now let me write down what that looks like. We'll denote that. So we're talking next about rotational kinetic energy. I'll write it over here, K ROT. Now we have to go back to another topic from 110, Physics 110. So just like we had 1/2 mv squared for translational kinetic energy, we studied rotation last semester, and we had a formula for rotational kinetic energy. 1/2 times the rotational inertia, or moment of inertia, I, times the angular velocity, omega squared. Except now you can have rotation about an x-axis, so there can be an omega sub x, and rotation about a y-axis, omega sub y. So K rotational for this kind of barbell-shaped molecule is 1/2 I times omega x squared plus omega y squared. But no omega z, because you cannot detect the rotation about the bond axis. That's quantum mechanics. Okay? All right, now that's a blast from the past, but we still need it. We also need another idea from the past. We can relate angular momentum component to angular velocity component. The x angular momentum, L sub x, is equal to the rotational inertia times the x angular velocity, omega sub x. Don't say W, omega. With a similar equation for y. Which means, with that idea, that we can write the rotational kinetic energy in the form 1/2I times Lx squared plus Ly squared for a diatomic molecule. And that then there is 1 and then 2 squared terms. These are angular momentum components squared, but there's 2 of them. So we get 2 degrees of freedom, F equals 2, from the rotational kinetic energy. So if the diatomic molecule is both translating and rotating, there's 3 plus 2, or 5 degrees of freedom. But that's still not all. There's another kind of motion that could, in principle, occur with our diatomic barbell-shaped molecule. And that's another topic we discussed last semester. Oscillations, or vibrations, they're also called. You can imagine, here's the bond again, with a hydrogen atom at each end, that the bond is like a spring. In fact, that's very much how you can think of it. It's like a spring. Quite a stiff one, but it's like a spring, which means it can be made to oscillate. And so the whole molecule can do this. Okay? And there's energy associated with that. Now, there's actually 2 kinds of energy associated with that. There's kinetic energy from the oscillation or vibration, but there's also potential energy from the spring. Now, the oscillation energy goes like p squared over 2m, momentum squared over 2 times mass. And the potential energy goes like the spring constant over 2 times the amount of stretch or compression squared. The point is that energy from the vibration has 2 squared terms, one from the kinetic energy and one from the potential energy. So the vibration of that bond along the molecule gives 2 more degrees of freedom. So altogether, for a diatomic molecule, there could be 3 degrees of freedom from the translation of the molecule as a whole, 2 degrees of freedom from its rotation, and 2 degrees of freedom from its vibration. Now we'll have to talk about when those various degrees of freedom are observed, but that's how many you can, in principle, have for a diatomic molecule. Now you could have what are called polyatomic molecules. We won't spend a lot of time talking about them, but that means any molecule with 3 or more atoms bonded together. In that case, things get even a little bit more complicated, but I'll just talk you briefly through. For the translation of the molecule as a whole through space, you have 3 degrees of freedom because it's 3-dimensional space. For the rotation, you can actually have 3. You can have rotation about all 3 axes, x, y, and z. So the rotational degrees of freedom can go to 3. And the vibration can be even more complicated, depending upon how many molecules there are. So with polyatomic, it can get pretty complicated. We're not going to spend much time talking about that. We're going to talk about, actually, monatomic gases, where you just have individual single atoms, and diatomic gases, like H2, hydrogen, where you have diatomic molecules zipping about. All right, let's go from there now. Let's start by writing down a simple formula for the total internal energy of such a gas. And we're going to use the equipartition theorem. Okay, so this result comes from the equipartition theorem. Remind you what the equipartition theorem says. For every degree of freedom, every molecule has an average energy of 1/2 kBt. So, for the total internal energy of the gas, we take 1/2 kBt and multiply it by 2 things. There's the 1/2 and the kBt. F, how many degrees of freedom does each molecule have? And capital N, where that's the number of molecules. Yes? And that will give you the total energy, right from the equipartition theorem. So here's the way we would often write it. F over 2, capital N, kB, T. T is the absolute temperature in Kelvin. Please remember that in terms of counting, if you have that combination, capital N times kB, total number of molecules times Boltzmann's constant, you can replace it with little n, number of moles of the gas, times the gas constant per mole, R. So perfectly equivalent way to write the total internal energy is F over 2 little n RT, either way. Okay, this is a very important and useful relationship for the total internal energy of an ideal gas. You need to know 3 things. How much gas do you have, either in terms of big N or little n? How many degrees of freedom does each gas molecule have, F? And what's the temperature in Kelvin, T? All right, now with that, armed with that result from the equipartition theorem, we're going to get back to the question I started with. Got a gas, ideal gas in a container. We're going to add energy as heat Q under specified conditions and figure out how much the temperature changes. So here we go. For that, we will need to talk about the concept of molar specific heat, and let's start with constant volume. Okay? We're going to do this experiment by holding the volume of the gas constant. I'm going to give you the symbol I'm going to use for molar specific heat at constant volume. That's my notation. Little c, subscript m and v. M because it's a molar specific heat, and V to remind us that we're holding the volume constant. I'll just give you a head up, if you read in the book, the author's notation for that same quantity is capital C sub V, but I don't like it. So I'm using little c mv. So here's the question. How much energy must be added as heat Q to little n moles of a gas at constant volume? We're going to stipulate that we're going to hold the volume fixed to produce a temperature change delta T, T2 minus T1, T final minus T initial. The starting point is the heat absorption formula from chapter 18. Q is related to delta T in that form. Number of moles times molar specific heat at constant volume times the temperature change. So that idea right there comes straight from chapter 18. All right, we're going to insert that expression with the first law into the first law of thermodynamics. Here's the first law. The internal energy change of any system is equal to the energy from heat minus the work done by the system. Q minus W by. And now we substitute for the Q. Okay? And we get this expression right there. So far, delta E internal equals N CMV delta T. Minus. Now, what's going on with this minus 0? You see why I put that there? Well, that's the W by contribution. We're saying W by is 0. There is no work done by the gas in this experiment we're thinking about. You see why? Because the volume is constant. And for a gas to do work, its volume must change. So in a constant volume process experiment like this, there is no W by. That makes the first law a little bit simpler. The internal energy change is purely from this heat transfer Q. Now what I do is I use the equipartition theorem to write the formula for delta E internal. Use what I have up in the box right up above. F over 2 little n R delta T. That's from the equipartition theorem. So now the formula is this, we're at this line. Now divide both sides by n. And then divide both sides by delta T. And you have a very simple formula for a very specific situation. It's the molar specific heat at constant volume. And it really only depends on one thing. How many degrees of freedom, F, does each molecule have? Because the molar specific heat at constant volume is F over 2 times the gas constant per mole. Look how simple that is. Easy to work with that. We'll be applying this kind of thinking to our first in-lab experiment coming up next week. All right, now that's an experiment where we added energy as heat Q and we held the volume of the gas constant. Now I want to imagine a second kind of experiment. We'll only imagine two. We're going to add the energy as heat Q, but we're going to stipulate that the pressure of the gas must be constant. Pressure, which we can do with our little apparatus I've been talking about. So now we're going to introduce the concept of molar specific heat at constant pressure. Here's my notation. Little c, subscript m for molar and p for pressure. Here's your author's notation. Big C sub p. I don't like it. All right, here's the question. How much energy must be added as heat Q to n moles of a gas while its pressure is constant to produce a temperature change delta T, T2 minus T1, T final minus T initial? Answer comes from the heat absorption formula from chapter 18 that relates Q and delta T, but now we write it like that. Q equals little n times the molar specific heat at constant pressure times delta T. All right, our goal here will be to work out a formula for CMP. Before we do that, I want to show you a PV diagram, a pictorial way to think about the things we're talking about. Okay? Because pictures, learning by pictures, is also a valid and useful thing. So we have a PV diagram, pressure plotted versus volume, for an ideal gas. And the starting point is going to be right here. I'll make a nice big dot with a volume V1, pressure P1, temperature T1. So I've even drawn there in the blue, that blue curve, the T1 isotherm, which remember is a parabola. It's of the form y equals a constant over x that passes through point 1. And that's our starting point for our ideal gas. And now let's imagine the two experiments I've been thinking about one by one. First experiment we talked about was adding energy as heat, Q, to get the temperature to go from T1 to T2 while holding the volume constant. That's this path right here. Straight up until we get to that point on the T2 isotherm, with T2 higher than T1. Okay? That's the constant volume process with no work done because there's no area under that line I just drew, right? And all the energy added as heat, Q, goes into increasing the internal energy in the constant volume case. Now imagine the second experiment, still starting at the first point, point 1, but now add energy as heat and keep the pressure constant until the temperature goes up to T2. Now you go straight horizontally to the right until you hit the T2 isotherm. That's a constant pressure process. And now, to get from the T1 to the T2 isotherm, the gas expands to a new volume, V2. And it does work. And the work is represented on the PV diagram by that shaded area, right? Which is just a rectangle of a certain height and a certain width. Okay? So now when you add energy as heat, Q, two things happen. The gas expands, so work is done, W by, and the internal energy goes up. But you can see already that you're going to need more heat in the constant pressure process to go from T1 to T2, because some of that Q is going to do work, which is not the case in the constant volume process. All right, so now continuing with this whole discussion of the constant pressure experiment. Go to the first law, thermodynamics. It's a very general statement. Delta E internal equals Q minus W by. And now use the formula that relates Q and delta T, if the pressure is constant, in CMP delta T. And then, here's another thing that we're going to do. W by is positive, the gas expanded, and it was the area of that rectangle right up there, which is just the height, which was just, I'm just going to use the symbol P for pressure, and the width I'm just going to call delta V, change in volume. I don't want to call it P1, I just want to call it P. And delta V, and that's that shaded area there. So, for the work, it's just the area of that rectangle, P delta V. Okay? Next step, use the equipartition theorem and replace delta E internal with F over 2, little n, R delta T, equipartition theorem. And then we have, from the first law of thermodynamics, that relationship. Now, it looks a bit messy, but divide both sides by n. There's an n in every term. Divide both sides by delta T. There's a delta T in every term. And the formula at this point looks like this. I'll write it over here to the side. F over 2R equals CMP minus R. Now solve for CMP. Right? That's not hard. CMP equals F over 2 times R plus R. And factor the R, and you get this nice little formula right here. That's also pretty simple. The molar specific heat at constant pressure is F over 2 plus 1, all times R. But F over 2 times R, like I had here, that's the molar specific heat of the ideal gas at constant volume, right? So another way to write CMP is that it's CMV plus R. CMP is larger than CMV. It takes more heat energy to get the temperature change at constant pressure than it does at constant volume, for the reasons I said up above. Because at constant pressure, not only does Q go to make the internal energy, the temperature to go up, some of it's being used to do work. But whether you're worrying about CMV or CMP, it really all boils down to knowing F. How many degrees of freedom does each molecule have? That is a key question if you're talking about molar specific heats for an ideal gas. So now I want to show you how to think about F a little more. And I want to show you a representation of actual data. It's not taken from an original literature, but it's a representation of original literature, actual data from actual experiments for hydrogen gas, since we've been talking about that as our kind of example of a diatomic gas, okay? And I want to show you how the degrees of freedom, F, for the diatomic gas, are quote-unquote turned on as the temperature increases. So it may be a little hard to see, but the vertical axis is molar specific heat at constant volume divided by R. Our results tell us that that is nothing more than F over 2. The number of degrees of freedom divided by 2. That's going to be plotted on the vertical axis, the y-axis. The horizontal axis is temperature in Kelvin. It happens to be a logarithmic axis. Do you see the spacing of the grid lines shows you that? They just plotted it that way so that you could get a very long range in a compact graph. That's one of the reasons you make an axis logarithmic. One of them is if your data follows over a very long range. To use a linear scale would mean you need to draw a very long axis. But a logarithmic scale can do that much more compactly. And then the curve here is in green, the representation of the data. Here's the point. At lower temperatures, pretty low on the Kelvin scale, it goes down to 20. It doesn't go below that, because if you start to go below that, you discover that the hydrogen gas liquefies into liquid hydrogen. We're not worrying about that. But at low temperatures, 20, 30, 40, 50, up to a little below 100 Kelvin, the data for CMV over R, right there, is at the value 3/2. In other words, F equals 3. Yes, F equals 3. What is that coming from? The translation of the H2 molecules. They're just translating throughout space, and nothing else. But as you increase the temperature from 100 up to 200 and go high enough, you reach this plateau up here, which includes room temperature, by the way, 300 Kelvin. And on that plateau, the value on the vertical axis, right there, is 5/2. Or F equals a total of 5. What's happening there? Well, you've got the 3 degrees of freedom from translation of the molecules throughout the container, and 2 more degrees of freedom from, it turns out, rotation. That's where you get the 5. 3 degrees of freedom from translation and 2 from rotation. Experiments tell you this. And the reason the rotation doesn't occur at low temperatures is because of quantum mechanics. And in quantum mechanics, the rotation, when you study that, you discover there's a minimum energy possible. And if you don't have enough energy to be at that minimum, you can't have any rotation at all. But as the temperature gets high enough, then there's enough energy to have rotation as well. But you always have translation. Now, if you take the temperature of the gas higher still, go way above room temperature, start to get more at around 2000 Kelvin, then you see that the data starts to transition up to another plateau at 7 halves, which means F equals 7. 7 degrees of freedom. From what? 3 from translation, which you always have, 2 from the rotation, and now you've turned on the 2 more from vibration. Okay? But you have to get to a very high temperature for that to happen. And in fact, what you discover is when you start to get to those high temperatures, there's so much energy that when the molecules bounce into each other, they break apart. It's called dissociation. So, bottom line, for a diatomic molecule, you're not likely to see vibration. It might be possible, but it's not likely. What you are likely to see is translation with F equals 3 at very low temperatures. And if you're at room temperature, translation plus 2 more degrees of freedom from rotation for an F of 5. So you do need to be aware of the temperature of your diatomic gas. That way you'll know what the F is. Okay, I want to close the video with a kind of a table summary, a graphical summary of the key ideas. And let me try to talk you through. This is right out of your book, but it needs some talking. Okay? Because it conveys a lot of information in a compact picture, but you have to decode it. All right, let's start by looking at a monatomic gas. That would not be hydrogen. An example there might be any of the inert gases, like helium, He. Helium, in the gaseous state, is just a bunch of individual helium atoms zipping around. And because of the complicated nature of interatomic forces in helium, they don't tend to bond into helium-2 molecules. They remain monatomic. Let's talk about a monatomic gas. You could also have in this column a diatomic gas that's very cold, so that only translation is happening. That's also possible. But I'm focusing here on the left side of this diagram. And I'm going to start at the bottom. Imagine the experiment where we add energy as heat, but we keep the volume constant, Q at constant volume. Then the formula for Q, or that relates Q to temperature change, is number of moles, molar specific heat at constant volume, times delta T. Then make a substitution for CMV of F over 2 times R. Now the only thing that can be happening here is translation, so F is 3. So 3 halves R for the CMV, and you get the formula Q equals 3 halves NR delta T, which is what is written right here. And all of that energy as heat, Q, goes into increasing the internal energy of the gas through its translational motion. That's what this is saying. And here the formula for delta E internal from the equipartition theorem is F over 2 NR delta T. 3 halves NR delta T. The same as the Q formula, because all of the Q went to the delta E internal. All right, now let's move our way up on the left side. Let's do an experiment with the monatomic ideal gas where we add energy as heat at constant pressure, P. So now the formula for Q is Q equals N CMP delta T. But now use the formula for CMP, F over 2 plus 1, all times R, where the F is 3. All that a monatomic atom can do is translate. F is 3. 3 halves plus 1 is 5 halves. So the CMP is 5 halves times R. So the Q formula is 5 halves NR delta T, which is this higher number, 5 halves NR delta T. For Q. Now that energy as heat, Q, goes into two things happening, as this shows. Some of it goes into doing work, and some of it goes into increasing the internal energy through the translational motion. This part, delta E internal from the translational motion, is 3/2 n r delta t from the equipartition theorem. And therefore the work must be nr delta t, so that I have 3/2 nr delta t plus nr delta t to get the total Q, 5/2 nr delta t. And that's all that can happen. So full stop for monatomic gases. They can only translate. And that's it. Okay, now the right-hand side is about a diatomic gas at room temperature, so that the molecules are both translating through space and rotating about 2 perpendicular axes. And you can take such a diatomic gas at room temperature, and you can add energy as heat Q, starting first at constant volume. So then again, you start with the formula Q equals N CmV delta T, and you write use our result for CmV, F over 2 times R, but now the F is 5, because the diatomic molecules can translate through space, F equals 3, and have rotation about 2 axes, so that's 2. 3 plus 2 is 5. For the CmV then, we substitute 5/2 R, and the Q result we get is 5/2 nr delta T. And that's the level at which they've drawn it, right? There it is, 5/2 nr delta T. Now, all of that energy as heat, Q, all of it, if V is constant, goes into increasing the internal energy. That in turn gets divided because it goes into increasing the energy due to translation of the molecules and due to rotation. Just to be clear, the energy change that goes into increasing the translational motion is 3/2 nr delta T, because there are 3 degrees of freedom. And the energy change that goes into increasing the rotation is 2/2 nr delta T, or 1 times nr delta T. Okay? Okay, that's what happens if the volume is constant in a diatomic gas. And then lastly, let's add energy as heat to the diatomic gas at constant pressure. And let's figure out that Q formula. Q equals N CmP delta T. But now use the CmP formula. F over 2 plus 1 all times R, where F is 5 again, right? 3 degrees of freedom from translation and 2 from rotation. 3 plus 2 is 5. So 5/2 plus 1 all times R, which is 7/2 R. So the Q formula is 7/2 nr delta T. And that's higher up, and that's right here. Think of this going up as like an energy axis. Going up is higher energy. Now, this is a constant pressure experiment. Sorry, that was cut off there for you, wasn't it? There we go. How about that? This is a constant pressure experiment, so the energy added as heat, Q, goes into doing 2 things. Lets the gas expand and do work, and increases the internal energy. And the internal energy increase is further subdivided into increasing the energy associated with translation and the energy associated with rotation. And with the translation, you have an associated energy change of 3/2 nRT. And with the rotation, you have an associated energy change of nRT. And with the work, you have an associated energy change of nRT. 3/2 nRT plus nRT is 5/2 nRT plus another nRT is 7/2 nRT. That was the Q. So that's what this table is trying to show you. It's It's trying to encapsulate all of this content. You may need to think about this a while. You may need to, and that's the beauty of these videos. You can pause, you can rewind, you can listen to me say something again. Okay? But it's just a way to summarize all of the information that's in this video. Okay. All right. Now, the last thing is a class engagement exercise that you will answer on Blackboard, as usual, to let you practice with these ideas a little bit. Practice with molar specific heats and degrees of freedom. Here's a scenario. There are 3 ideal gases, all with the same number of moles, little n. And they're all going to undergo a constant volume processes, with the same temperature change, delta T. So a lot of things are the same. But here are the different gases. The first one is a monatomic gas, maybe helium, for example. You have n moles of it and undergoes a temperature change, delta T. Second gas is a diatomic gas without rotation of the molecule. So that might be hydrogen H2 at very low temperatures, like 50 Kelvin. And the third gas is a diatomic gas with rotation. Let's say hydrogen gas at a room temperature of a warm room, 300 Kelvin. Those are the 3 gases, all have the same number of moles. We're all going, in all 3 cases, we're going to add energy as heat Q to get a specified temperature change, delta T. Maybe 10 Kelvin, for example. All right, A. Rank the processes 1, 2, and 3 according to the molar specific heat at constant volume, CNV, greatest first. B. Rank the processes according to the value of the change in the translational kinetic energy, delta K tran, or trans. Translational kinetic energy, greatest first. And lastly, rank the processes according to the value of the change in the internal energy, delta E internal, greatest first. Those are the 3 questions for this class engagement. And then we'll have a class video where we will apply these ideas. But that's all for this video.